Hello, I welcome you all to this another interesting screencast, and the problem reads the thin ring can be adjusted vertically between three equally long cables from which the 100 kg chandelier is suspended. If the ring remains in the horizontal plane and Z equal to 600 millimeters, determine the tension in each cable. The second problem reads the thin ring can be adjusted vertically between three equally long cables from which the 100 kg chandelier is suspended. If the ring remains in the horizontal plane and the tension in each cable is not allowed to exceed 1 kilonewtons, determine the smallest allowable distance Z required for equilibrium. Both these problems are coming from the Engineering Mechanics and Statics textbook, 13th edition by R.C. Hibbeler. So we have a chandelier supported by three cables that are spaced equally. Okay, and this just simply means there is a symmetry. There is symmetry about the Z axis. Okay, so if you've seen here, we have these, they are spaced equally here, being measured by these angles 120 degrees and 120 degrees. So it's like we can cut these portions that are equal. Seeing these portions, they are all equal, right? All right, so this makes this particular system symmetrical. So because of symmetry, and assuming all other factors remain constant, we expect the tension forces. AB equal to AC equal to AD equal to, let's call it T. Okay. So now what we need to do now is let's section this so that we draw the free body diagram. Great. So we've been told that this chandelier weighs 100 kg. There we go. We are going to indicate that later on. So we have a tension force there, and then like so. Okay, and then we have another tension force there like so. Okay, and then we have another tension force like so. All right, there we go. So we have these tension forces that we are going to label. Let's start with this. So this is 100 kgs. So let's convert it to newtons. So we are going to multiply this by the acceleration due to gravity. So 100 times 9.81 meters per second squared, right? So what does this give us? When we multiply this, it gives us a 981 newtons, right? Of course, this is AB, this is AD, this is AC, AC. All right. What else do we need to know? All right, this one has obscured visibility here. So this is also AC. This is AC. Okay. All right. So what we need to do now, we are already concerned with the vertical components. So let's find the angle, right? The angle, and the angle also, the slope also is going to be vertical slope also, we expect it to be the same. So what we need to do is let's find the length. The length AB equal to the length AC, which is equal to the length AD, and it's just going to be equal to the square root of Z, okay, is equal to Z squared, okay, plus the radius of the ring where the cables are attached, and the radius is equal to 0.5 squared. So this gives us, let's do the multiplication. 0.5 squared gives us what? So this is just going to be equal to, so the length therefore, let's call this, let's just call this L as equal to that. Therefore L is just equal to square root of 0.25 plus Z squared. Okay, so we have that. So let's now find the components of this particular force. Of course, we're interested in the vertical components. So let's start with AB. So we expect AB like so. We don't have along the x-axis because this is in the y component. It's just in the one plane, AB. So we just expect it in the y, just in the y and z. Okay, that's fine. Right. It's just it's just in two in a single plane. AB is in the, it's just in the x, in the y z plane. Okay. Right. Then let's work out the other ones. So we expect also AC to have a component in this direction. Let me just indicate in this direction. Okay. And where is AC? AC, it is that side. So when we look at AC, it will have a component both in the x and in the y, right? So where is it? It is there. So let's establish the angles. Let's establish the angles. So what we need to do is to extend the coordinates. Let's extend these coordinates. Let's extend this coordinate here. Sorry. What we need to do is to extend these coordinates. Okay, this is our y. Okay, and this is our x. All right, and then what do we have? So from there to there. Okay, so this angle here is equal to, this is equal to, that's 120 minus 90, this is 30. Okay, and then this one here, this one is equal to 60. Okay, and then this one here, this is equal to, So if this is 60 and then the rest of this was 120, so this is going to be equal to a 60. This is going to be equal to a 60, right? So if this is part of it is 60, then what remains there becomes a 60 as well. So I think this is enough, because if we can find one, then we can find the rest. Great. I think this is fine. So now we are good. We're good to go. So we said we are on AC. So AC, we expect a component in the negative along the y, in the negative along the y, okay, along the y, and then we also expect a negative along the x, right? Along the x. All right, great. And then finally, we have another component which is in the z for AD, and AD we expect a component, a positive along the x, right? Expect a positive along the x, and then we also expect uh, uh, a positive, I mean a negative. We expect a negative along, so along the x a positive, then along the y we expect a negative, right? We expect a negative, like so. All right, so let's label those. We start with AB. AB, we said is only in the YZ plane. So in the Y we'll have AB. We'll have AB by by the length, which is in the Y, it is just a 0.5 divided by root of 0.25 plus, okay, let me call this as A star, okay, or yes, just A star, okay, so that I avoid this long jargony. So this will just be equal to 0.5 divided by this A star, okay, and then this component is just going to be equal to AB by the length along the y-axis. Mind you, our reference, we didn't mention our reference. Our reference is A, which is a 0, 0, 0. So AB here is the height Z divided by A star, okay, and then we go to AC. Where is AC? So AC, there we go. Along the x-axis, AC is just going to be equal to 0.5 divided by A star and then we need to map it. You've seen here, we need to map it along the x-axis. Okay, we need to map it along the x-axis, which is this side like that, right? Okay, so mapping it in that direction will give us sine 60 degrees. All right, and then AC along the y-axis is again 0.5 divided by A star. We map it along the y-axis, which is just cos 60. And then later on, we have AD, which is just Z divided by A star. And then we have AD there. We have AD. We have AD along the x-axis, AD by 0.5 divided by A star. And then when you look at this, we are mapping it. You've seen here, this is AD here. We are mapping it like so. Okay, we are mapping it here. Okay, we are mapping it like so. Okay, so to map it, this is going to give us a cos 30 degrees. And this component is AD 0.5 divided by A star, and then we map it also. There is no space. Alright, let me write it down here as AD 0.5 divided by A star. Okay, and then we map it on the y-axis, so we are mapping it like this. Okay, so once we map it, that becomes sine 30. Alright, so I think we are done with all of those, all the cases, right? We are done with all the cases. Great. Okay, I think we remained with one, this one. Alright, so this one is AC Z A star. Great, so let's write down the equations of equilibrium. So we have summation of forces in the x equal to 0. So in the x, what do we have? We have the 2. Course in the x we have this, and then we have the other one. So this is going to be equal to, let's say AC, start with AC, negative AC, so negative 0.5 divided by A star, sine by AC sine 60 plus AD, I mean 0.5 divided by A star, AD cos 30 equal to 0. Okay, so from this equation we know that cos 30 is the same as sine 60, right? These are the same. So from this we know that from this equation cos 30 is equal to sine 60 like we said. Therefore, AC is just going to be equal to AD like we said. So let's go to the other equation, which is summation of forces in the Y. What do we have in the Y? Okay, this one in the Y. In the Y we have the following. So AB, so 0.5 divided by A star AB minus 0.5 divided by A star AC cos 60 minus 0.5 divided by A star AD sine 30 equal to 0. Okay, so we know that AC is just equal to AD. So what we are going to do is we just replace this one there. We replace this there. And when we do so, we also know that when we do so, then we realize that AB is just going to be equal to we also know that cos 60 is just equal to sine 30, and therefore AB is just going to be equal to AD, okay, AD by 2, alright, plus another AD that side by 2, which is just equal to AD. Therefore, AB is equal to AD, which also therefore is just equal to AC. We are just proving this point, right? Alright, so then summation of forces in the Y, in the Z, which is so we have AD. So this we can just say this is equal to T, like we said. Okay, so the summation of forces there, it will just be equal to 3T times Z divided by A star, okay, minus 981 equal to 0. Okay, so let's go to case, we go to case 3-63. Alright, so here we've been told that Z is equal to 600 millimeters, okay. Z is equal to 600 millimeters, so we need to convert it to meters, which is just 0.6 meters. So if that is the case, then our equation here will become T by 0.6 divided by root of 0.25 plus 0.6 squared, okay, then this is just going to be equal to 981. Okay, so T gives us, let's calculate it. So 0.25 plus 0.6 squared, okay, root of that, then 0.6 divided by answer, then times 3, 981 divided by answer. So we have T equal to 425.6566 newtons. Okay, 66 newtons. Let's repeat it. So 0.25 plus 0.6 squared, then 0.25 plus what was 0.5 squared plus 0.6 squared, root of that 6 divided by answer, okay, times 3, so 981 divided by answer, so 42. So this gives us a 42.57 newtons, right? So 0.6 divided by root of 0.25 plus 0.6 squared by 3, then 981 divided by answer, 0.25 plus 0.6 squared, square root of that, 6 divided by answer by 3, and then 981 divided by answer, 42.57. Alright, so found what the tension in each cable is. This is, therefore we are saying AB is equal to AC, which is equal to AD, which is equal to a 42.57 newtons. Alright, so let's find the value of T. So we are going to say AB. What do we have here? So we have the following. We have 3T. We have 3T times Z, which is 0.6, divided by A star, and A star is nothing but 0.25 plus 0.6 squared. So this is equal to 981. Therefore, AB, which is equal to AC, which is equal to AD, which is equal to T, is finally equal to, let's calculate it. So 0.25 plus 0.6 squared, root of that 0.6 divided by answer by 3, and then 981 divided by answer. So we have a 425.66 newtons. Alright, so that is the solution for the tension in all the cables. So let's move on to the second case. We move on to the second case. Okay. So what is the second case? That is case 3-64. Okay. There we go. So in this particular case, we are being told that Z is equal to, here we are being asked to find Z. Given that the maximum tension T maximum is equal to 1 kilonewtons. Alright, but the chandelier weighs the same weight. So we are going to use this same equation, 3T Z divided by root of 0.25 plus Z squared equal to 981. So what we'll do is we are going to replace this maximum here, replace it there, and once we do so, then we are going to have the following expression. I'll have the following expression. we'll have 3,000 Z equal to 981 root of 0.25 plus Z squared. We've converted this into newtons. That's the reason it's 3,000. So we are saying this is also equal to 1,000 newtons. Okay, because 981 is in newtons. So we are going to square this both sides like so that we get rid of the square root. So this becomes a 3,000 squared Z squared equal to 981 squared by just 2.5 plus Z squared, like so. Alright, so simplifying this becomes a 3,000 squared Z squared minus a 981 squared by Z squared, okay, equal to 981 squared by 0.25. Okay. Alright, let's calculate Z. So Z is just going to be equal to a plus or minus. So we have 3,000 squared minus 981 squared. Okay. And then we have 981 squared times 0.25 divided by that, and then square root of that. Then we multiply it by 1,000 to just convert it to millimeters. So we have a 173.01 millimeters. Of course, our Z is positive, therefore our Z is just going to be equal to 173.01 millimeters. Right. I think we are done. We have AB there, like so. We have AB, which is equal to AC to AD, and then we also have the smallest allowable distance, Z, 173.01. So I hope the video was helpful, and if it was, give me a thumbs up, like my video, continue subscribing and liking my channel. Bye bye, and see you in my next screencast.